Okay, so for our thing, we started talking about Democritus. Did you see this already? Okay, so Democritus is what we would consider the very first person to ever have any sort of theory that we would sort of consider modern chemistry. And what he did was propose just the idea that there were atoms, right? And that's all he did. Before that, people thought that if you took something that was made out of matter and you kept cutting it into smaller and smaller pieces, you could do that forever, right? And there was no piece that was so small you couldn't cut it. And what Democritus said is there has to be something that's so small that when I try and cut it in half, if I do, it's no longer what I started with, right? So if I have gold and I keep cutting it, there must be a particle so small that if I cut it in half, it's not gold anymore. And so he came up with the word atomos, which in Greek means indivisible, and that's where we get the word atom from. After him, we have something called alchemy for like the next 2,000 years. Aristotle had this theory that there was 4 elements, the ones on the left over there, air, earth, fire, and water, and that you could mix those 4 things together in different proportions and make different things. It was really kind of a dumb idea because it was really easy to prove wrong, right? His one idea was that because humans were the most important and complicated thing on Earth, that we were equal parts of all of those, which meant if you mix those 4 things all together equally, you should get human flesh, which you could try, and it wouldn't work, and it should have proved the theory wrong, but it wasn't really science back then, right? So people believed him for a really long time. But after that, people realized that you could make a lot of money if you could do certain things, and the main thing they wanted to do was be able to turn other metals into gold, right? Because you could find lots of lead and copper and that sort of thing, but it wasn't worth as much as gold. So the idea was if we could invent something or find a process that would convert copper and lead and those other metals into gold, we could make a lot of money. And that's where alchemy comes in. And so as kind of pointless as that was, because you can't do it, it turned out that it got us all of the sort of operations they have on the side there, right? Filtering things, mixing things, boiling, distilling, all the stuff we normally associate with chemistry was sort of piloted by these people. It didn't move forward very quickly because those people were really secretive, right? Because if I was an alchemist and you were an alchemist, when I discover how to make gold, I don't want to tell you. So there was no sharing and collaboration. Like nowadays, I make a discovery, I publish it so everybody can see it, and then we keep moving forward. Back then, if I made a discovery, I was the only person that knew it, so if I died, it just disappeared. And so it moved forward really, really slowly. But then we get John Dalton. By John Dalton's time, we have enough evidence that we've decided that we can we've decided that we need actual experiments, right? So we need to run an experiment and record data and that sort of thing. And Dalton wasn't really a scientist, he was a school teacher, but he realized he needed to explain how matter works to his students. And so he took all the research he could find and put it together into one theory, and which is why he gets something called the billiard ball model sort of associated with him, because he was the first person to describe it. And it has 4 postulates. The first one is that elements are composed of small indivisible particles called atoms, which is still true, right? Now we can divide them because we learned that in the nuclear chapter, but for the most part, indivisible. The second one is that atoms of the same element are identical and atoms of different elements are different, which is sort of true. Every atom of one element has the same number of protons, right? So every carbon has 6 protons, every oxygen has 8, that sort of thing. But we learned later on that the electrons and the neutron number can change. He said that the atoms of different elements combine together in simple proportions to create compounds. This is true, right? You take 2 hydrogen to every 1 oxygen, you can make water. If you do 2 to 2, you get hydrogen peroxide, right? You take 1 sodium to 1 chlorine, you get table salt. So we're just mixing them in normal proportions. And then he said, in a chemical reaction, atoms are rearranged but not changed. So this is law of conservation of mass. So we take hydrogen and oxygen, we put it together and make water. What this is saying is we combine the hydrogen and the oxygen, but there's still hydrogen and oxygen there. And we haven't created any new hydrogen or new oxygen, we just move them around, right? Just like if you have a bucket full of Legos and you build a castle, at the end you have the same number of Legos, right? They're just rearranged to take some functional shape. Okay. And so that's what he's saying there. And then after him, we get Henry Becquerel, which for this chapter you don't really need to worry about, but he's big in the next chapter, the nuclear stuff, right? I just wanted to put him in here so people sort of realize where that discovery was made. And then we get J.J. Thomson. And J.J. Thomson discovers something, or uses something called a cathode ray tube. If you've ever gone to the gag gift stores and stuff in the mall. They have those glass balls that have the little purple, looks like lightning in them, and you put your fingers on it, it moves. Yeah. Okay, so his was basically like that, except it was a long tube, and it had a positive charge at one end and a negative charge at the other. And he would see those beams, right, like that purple beam in there, and he realized that these things were made of negatively charged particles, and that he could pull that beam out of almost any element he put in there. So he realizes this isn't a new atom, this is something he's pulling out of the atom. So for the first time, instead of them being these round spheres like Dalton thought, there's something inside. And basically what he finds out is he discovered electrons. And he ends up with something called the plum pudding model, which looks like this. So he took Dalton's idea and said it's still going to be a sphere, right, a big ball, but now we have these little negative chunks inside of it. The problem was if there's negative chunks inside, the whole thing had to be negative, right? And so he realized that there has to be something positive to cancel out the negative, but they didn't know about protons yet. So what he said is that whole background is all positive stuff. So you think of it like a chocolate chip cookie, where each of the little chips is a negative thing, but then all of the dough around them is positive, so if they cancel out, they end up even, right?
Is that what we did with those little dots on the...
Yeah, that was part of what we're doing, yep. So this is his model, right? They call it the plum pudding model because he was British, and so they think of plums and pudding instead of chocolates and chocolate chip cookies, but either way, works. And then after him, we get Ernest Rutherford. He developed something called the gold foil experiment, which has a really thin film of gold that he shoots alpha particles at, which we learn about in the next chapter, right, with the radiation, but he didn't know what they were at the time. But the idea was that if the plum pudding model was right, those little alpha particles should shoot straight through this layer of gold and hit the other side. And for the most part, they do. But every once in a while, one bounces back. And so it's hitting something in there that's causing it to deflect. And what he realizes is two important things. Number one, that there's a nucleus, that there's this solid thing at the center of the atom that has a positive charge. And number two, that it is very, very, very small, because like 99% of things still head through. So he discovers the nuclear model, which just says that the positive protons are at the center, clumped in this very small space, and the negative electrons are around the outside. He doesn't really have any good organization of those electrons around the outside at this point. They're just outside of the nucleus. Okay. We don't know about neutrons yet, so those aren't in the nucleus quite yet. But this is the important part where we realize most of matter is just empty space. Then we get to Niels Bohr, who realizes there's a huge problem with that previous model, right? Because if I look at this previous picture, those negative electrons around the outside should get sucked in right to the positive ones, right? Because negative and positive attract each other. And so the question is, how do those electrons keep going around the outside without slamming into the center? And he developed something, and I'm not asking you to know, know exactly how this works, but he discovers that the electrons have quantized energy. What that means is they can have certain energy levels, but nothing in between. And there's a certain amount of energy the electron can never give away. So if I'm an electron, I want to get close to the nucleus, the only way for me to actually stick to the nucleus is to slow down and stop. And they can't do that. So he developed something called the planetary model, which is, people usually refer to it as a Jimmy Neutron model of the atom, right? That's sort of his drawing there. So you have the little nucleus inside, and then each electron has a certain distance away from the nucleus that it circles around.
Like
and
ring.
Exactly, like the planets around the sun, right? And so that's why we call it the planetary model. And the idea is that really low energy things end up getting sucked in and are really close to the center of the nucleus, or the center of the atom, and circle really close to the nucleus. And really high energy things end up much farther out. So big planets like Pluto, really far away from the sun, right? All right, so then we get to the very strange one. And this, for the most part, you don't need to know for the test. But Erwin Schrödinger finds out that you can't predict the locations of these things, which would seem really easy, right? Because we can look at where Mars is right now and think about, okay, how far is it going to travel over time? And you can tell me where Mars will be a year from now or 100 years from now. We couldn't do that with the electrons. And what we discover is that electrons, when we're not observing them, act like waves, which means they can be in more than one place at the same time. And so he developed something called an orbital, which is a way of describing the electrons based on the probable location. So we're not saying it's here and it's going to travel around to some new location. We're saying it's in lots of places at the same time, where is it likely to be when we look for it? Because when we look for it, it has to be in one spot. And so that's his sort of contribution. Again, you don't need to know a lot of that for the test. But he developed something called the electron cloud model. So now we still have the center. We've discovered neutrons at this point. But instead of saying the electrons are in one location, we just say, okay, they're in this hazy, weird cloud thing around the outside of the atom. Okay? During this time, James Chadwick has discovered the neutron. You don't really know about the Joliet-Curie experiments, but they prove the existence of the neutron and gives us the neutron model, which is basically the planetary model, except there's neutrons in the center. So.